Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry made easy. In this video, we're going to be looking at combining different spectroscopic techniques in order to deduce the structure of an organic compound. We're only focusing on infrared and mass spectrometry, and this combined with elemental analysis. So this is all AS or Year 1 of the A-Level Chemistry course. There will be another video that looks at Year 2 techniques that covers both proton and carbon NMR in tandem with all these different techniques. So we're going to delve straight in looking at an exam question. Now these questions with combined techniques usually account for about 6 marks in the paper, so they're quite weighty. Before we can actually start to tackle this, it's really important that you feel confident with elemental analysis, infrared spectroscopy and mass spectrometry. If any of these you're unsure about, make sure you've watched the appropriate video of those techniques and strategies on this YouTube channel before we start this. I just want you to pause the video here and have a read through the question and the data that's given. Okay. The strategy that you would want to tackle this question is, first of all, working out the empirical formula using the elemental analysis data. You've got this empirical formula. What you'd want to then do is to work out what the molecular mass is. And you're going to do this by looking at the molecular ion peak of your mass spectra. Now with this piece of information, the molecular mass and the empirical formula, you can deduce the molecular formula. At this stage, we're not finished with the mass spectra. However, what we would want to do is turn our attention to the infrared, as this is going to give us more information that then helps make life easier when working out what the fragments and the structure of our compound is when dealing with the mass spectrum. You've identified the infrared stretches. In the infrared spectra, you can work out what functional groups the compound has, and then you turn your attention to working out what the key fragments in the mass spectrum are. Having followed these steps, then you can use all the information to work out a structure for compound A. So pause the video here, follow the logical steps, and find the structure of A. Okay, so firstly, the elemental analysis. You can take the data from the question, divide these percentages by mass over the atomic masses. And what we do is we divide each of these numbers by the lowest number of moles. So here we have the lowest number being 2.275, so we're going to divide each of these by that number. That then gives us the following. You can see here that all we need to do is round up the 1.99 to 2, and the others are integers or whole numbers. So we have our empirical formula as C2H4O. Second step is then focusing on the mass spec, and the molecular ion peak here you can see is at 88. No, that means our MR is 88. In order to work out the molecular formula, we're going to use the fact that the molecular formula is 88 in mass and that the empirical formula works out to be 44. That's just the sum of 2 carbons, 12 each, 4 hydrogens, each weighing 1, and then oxygen at 16. And so we know that our molecule is going to be 88 divided by 44, 2 times the empirical formula. So we're going to take the empirical formula and times this by 2. This gives us the molecular formula that's going to help us going forward of C4H8O2. Now as soon as you see 2 oxygens within a molecule, you should start to think of those common functional groups that contain 2 oxygens in. It could be that we have a carboxylic acid. It could be that it's an ester. It could also be that you've just got a ketone or an aldehyde with another ketone or an aldehyde, or with an alcohol. And these would be in the same molecule. Here's an example here of a bifunctional molecule with a ketone in and then an alcohol in, and that would account for the 2 oxygens. This is why we go and try and identify any IR stretches that are going to either confirm or deny possible molecules with 2 oxygens in. Looking at this infrared, first of all, the 1740 is a really key stretch here. That is for a carbonyl group. The other key stretches, or absence of them, is there is no OH of an alcohol. Instantly, this allows us to rule out the possibility of it being a carboxylic acid with the 2 oxygens, or whether or not it's got an alcohol in it. We're most likely left with an ester, and we can just confirm this by the fact that actually here we have a distinctive CO bond present. And remember, these are all just using the data sheet and the patterns that we've learned in the infrared video. And so that CO bond is this CO bond in the ester. So with this information from the IR plus the molecular formula, we can start to have a look at the fragments in the mass spec. And so all the information so far has told us that we have an ester, and we know an ester is this Koch functional group, so it must have a carbon there, an oxygen, a carbon and an O. And we know that we have 4 carbons from the molecular formula that we worked out with the MR, the molecular ion peak, and the empirical formula. It's now going to be the key fragments that tell us how this ester could be formed. So we think about the possibilities of this ester. If I've got 2 more carbons, I could have 1 carbon on there and 1 carbon on there. Just put the hydrogens in. The possibilities involve having this carbon here actually on the left hand side, adjoined to here. We've got our ester functionality, but it's CH3 on the right hand side, and then we have a CH2, which is then connected to a CH3. There are 2 possibilities with just 4 carbons. What's really key here is this key fragment, and the fact that it's been identified is telling you that that is going to be a really crucial decider. Now, if we have a look at this, the C and the O right next to each other means it's a carbonyl. So if we just draw this out in a displayed formula, this is the fragment we are looking at. See, this could only be formed if the molecule was to break here. And then this form of the molecule is becoming a positive ion, whereas this form is becoming the radical. And so it is this that is actually being picked up by the mass spectrum, as only positive ions are actually registered. Remember, the radical isn't. Now it's this key piece of information and fragmentation that will lead you to the correct structure of A. See, if you tried to fragment the ester above, then you would not get either way. If you split it here, you would not get that fragment forming either side. And as we spoke about in the mass spectrometry video, remember, always look for a carbonyl or an alkyl and break towards the right or left of that bond. So always hone in to that group and split either side. So if you got to the stage of coming up with an ester but actually got this product instead, that would still get you into marks, but it's this use of the fragmentation that will get you to the 5-6 mark bracket to correctly identify that it must be A. Okay, now I want you to take this same approach with this exam question here. Obviously you're not given elemental analysis, so instead I want you to focus in on the information given in the question first, but then follow the same logical steps through to come up with a structure for compound J. So pause the video now and have a go. So first of all, with these types of questions, what you want to do is basically visualize what the information is telling you. So we know we've got an alcohol H with the molecular form is C4H10O, and we know it's being oxidized by potassium dichromate to form some sort of compound J. This in a more user-friendly form. Next, we're going to turn our attention straight to the mass spectrum and the molecular ion peak. In this case, that's the one that's furthest to the right, and then that gives you the molecular mass. Now it's important, even though this is small compared to this one, some of you might have been tempted to focus in on this peak as the molecular ion peak. It doesn't matter about the relative intensity or height of that peak, it's just the one that's furthest to the right. And this isn't small enough to be the n+1 peak. If it was, this peak would be even smaller, as only 1% of the compound would be registered at this value. This is too big, so it's definitely our molecular ion peak, and so our MR is 88. We can put this information for what we know about J. Definitely get in the habit of doing this in the exam, just pulling all the information step by step. Now we turn our attention to the infrared spectrum. So we're looking for any key peaks that will allow us to identify the functional groups. We have an extremely sharp, strong signal around 1700, and so we know this is a carbonyl. To be explained to the examiner, you know exactly what value that actually reads off at. And then also we have this incredibly broad peak here that is responsible for the carboxylic acid OH. With this information, we know that J must be a carboxylic acid, and it has originated from an alcohol with 4 carbons. Now, when you undergo oxidation, you don't add any more carbons on. So, it can be any one of these variations. Just add the hydrogens in, we can work out the MR. In both cases, these equate to 88. We follow the advice and always cut to look at fragments to see if we can identify which one of these two possibilities. And if we cut just to the left of the carbonyl in both cases, then this doesn't help us differentiate, because in both cases we have a C3 H7 fragment. C3 H7. This equates to 43. See this on the infrared there. However, what we are looking for is this molecule here can break this carbon-carbon bond here. This forms a peak at 29, which is this unit here. Can't get the same fragmentation pattern happen here because of if you had 2 carbons and split them, it would still have the rest of the molecule on it. So it is this fragment here at 29 that allows you to identify this as your identity for J. But actually in the mark scheme here it accepts either. Importantly, obviously you see this big fragment here. This is the fragment at 45, and responsible for that is the actual carboxylic acid functional group splitting away from the rest of the organic chain. And that's why it's such a big functional group, because again we've just cut to the left of our molecule. The other really big peak here at 87 is the loss of just a hydrogen in our molecule, leaving the rest behind as a positive. But again, both 45 and this can't help you differentiate between the two. So having identified J as butanoic acid, we need to be able to name alcohol H. So that would be if it's a carboxylic acid, the conditions must have been reflux and potassium dichromate and sulfuric acid. And carboxylic acids come from primary alcohols. So this must have been butan 1-ol. And so you can see how using information in the question plus the different spectra data leads you to understand how a reaction has gone and also work out reagents and conditions if required. So this concludes the video looking at using combination of different spectroscopic techniques and elemental analysis in order to deduce organic structures. Now this is only dealt with year 1 combined technique type questions. Year 2 A2 level chemistry is going to also sometimes require you to use nuclear magnetic resonance, or NMR, in the form of carbon-13 and proton H1 NMR, in order to come up with structures. If you found this video useful, ensure that you like it, and then ensure that you click subscribe so that you can get the new videos as and when they're uploaded.